Okay, first of all, let me say how that it is very nice to be here and to I'm really enjoying this conference. And what I want to do in my talk today is basically give you sort of like an update or like a status report of a project I've been engaged in for quite a while now. And it has involved the collaboration with a number of master students. Also, some discussions with John Berg and Richard Garner as well. So the eventual goal is to give a constructive account of the quantum-equivalent model structure on simplicial sets. The motivation comes from homotopy type theory. So the idea, of course, of type theory is that it is a foundation which should be simultaneously have a kind of topological interpretation, but also should have a computational interpretation. And so to bring these things together, the first step might be to understand the quantum-equivalent model structure from a constructive point of view. Now, the good news is that this has already been done. So Simon Henry, some people already referred to it earlier, has given a constructive proof of the existence of the quantum-equivalent model structure of simplicial sets. And in joint work with Nicola Gambino, Milo, and Christian Sadler, they have extended this to a model of Hot, maybe quasi-model of Hot, because indeed there are a few issues. So one maybe unsatisfactory aspect of their account is that in their treatment of this model structure, not every simplicial set is going to be cofibrant constructively. And also they don't have the result that if A and B are Kahn complexes, then A to the power B is also a Kahn complex. And in fact there's a result saying that this is not provable constructively. So basically what I'm hoping to get is an account of this model structure in which actually every simplicial set will turn out to be cofibrant, and in some sense we can still have the fact that a suitable notion of Kahn complex will be closed under exponentials. And my main tool that I want to use for this is the notion of algebraic weak factorization systems. And in particular, I think for the purposes of this talk, but also for the research that I'm doing, it is very useful to think about these objects. I mean, they're usually formulated in terms of interacting monad-comonad pair, but I would rather like to think about these things in terms of double categories. So, how does it work? Well, first of all, I think maybe I don't have to explain what a double category is. I mean, I have a set of objects, it carries two classes of morphisms, both giving rise to two category structures. And then in addition, I have whenever two like vertical maps, and so they're called horizontal and vertical maps, and whenever two horizontal maps and two vertical maps, it can be the boundary of a square. These squares can be composed both horizontally and vertically. There's a certain interchange law. In fact, they are internal categories in the category of categories. Maybe good to say that everything is supposed to be strict at this point, so I'm looking at strict double categories. There's one very canonical example. If I give you category C, I can just take the objects of C, then take for both the horizontal and vertical arrows, the arrows in C, and the commutative squares in C to be the squares, and I get a double category, which I will write like this. And I will say that a double category L is a double category over C if it comes equipped with a double functor from this double category to the double category of squares in C. Right. So the next definition I need is that of a lifting structure. So so the notion of lifting has been generalized. First from a set of lifting against a set of arrows, then against a category, and then further it can also be generalized to have a lifting structure against a double category. So let's say that I have a double category over C, a map in C. Then a lifting structure on this map F against this double category L is basically an operation which, given a vertical morphism in L, and commuted a square from this vertical morphism to my map F. Like a commuted square like this actually gives me a diagonal filler. And these are supposed to satisfy two compatibility conditions. So there's a map F with a set of fillers for all these squares in such a way that if you give me a square in the double category L, here I have such a lifting problem of L of G against F, then of course I get two solutions. I get a solution here for G primed and a solution here for G, and I want these things to be compatible, so I want this triangle to commute. Other compatibility, there's the horizontal compatibility condition and there's a vertical compatibility condition. So if I have a lifting problem of this form, I can do two things. I can first compose these sort of like vertical maps and then get a new vertical map in this double category L and there will be a filler like this. But also, another thing you can do is you can look at this thing as a square like this, then there will be a solution over here. Then this creates a new square like this, and there will be a solution over here. And you can ask these two things to coincide. So you get two maps from here to there, and the vertical compatibility condition is that these two maps should be identical. So, in fact, what happens is that if you look at all the maps which have a lifting structure against this double category L, they can also be organized into a double category. So we get a kind of orthogonal double category. So the objects of this double category L perp are those of C, the horizontal morphisms are those of C, the vertical morphisms are maps from the category C equipped to the right lifting structure against L, and then the morphisms, the squares in this double category are going to be maps of lifting structures. So I think of this square over here as like a morphism of lifting structures from F to F primed. And what that means is that if you give me a lifting problem over here, well, I can either consider this as a lifting problem of G against F prime to get a map here, or I can also, wait, is this correct? No, I think what is wrong. It's wrong here. So there's also a lifting problem of G against F. So there's a map over here as well. And then what we should have is that this triangle here commutes. So this dotted arrow should be here instead. And yeah, there's a dual sort of vertical condition, which basically explains how you can vertically compose maps which carry a lifting structure. So this picture is there's a kind of dual picture. So this explains how you can actually get a new double category over C out of the old one, and there's a dual story as well. So the definition of an algebraic weak factorization system that I will use, this is basically the definition that John Berg gives in his paper on an orthogonal approach to algebraic weak factorization systems as follows. I have an algebraic weak factorization system on a category C consists of two double categories over C. Then I need this sort of usual orthogonality condition, and I want a factorization. So every map in the category C should factor as a map which is a vertical map in this double category R, and here this lambda of F is a vertical map in this double category L. So I basically can write it as an L map followed by an R map in that sense. This decomposition is supposed to be functorial and have a certain universal property. And also there's a condition which says that, okay, so if you give me a square with a left map on the left and a right map on the right, this gives you a certain lift. This isomorphism gives you a certain lift. This isomorphism also gives you a certain lift. And the condition is that those two lifts should be identical. And you can always get a genuine weak factorization system from such a weak factorization system by taking the retract closures of the left maps in L and R. But So one thing that I basically want to do today is I want to explain actually maybe more clearly what I really want to do. Actually the slide in which I give the status report is just very short. So in some sense what I basically wanted to explain is not so much what I've done but what I would like to do. And then quickly explain how far I am. So in fact what I really would want to have is like an algebraic monoidal model structure on the simplicial set where the monoidal structure is actually given by the Cartesian product. So let's think about monoidal structure, monoidal algebraic Weak factorization systems for a moment. So this is something that I've been looking at also with John Berg. So usually I think the definition of monoidal model structure, well, involves squares like this. So you imagine that the category that you're looking at is a monoidal category. Maybe there is some map F which belongs to some class L0, a map G which belongs to some class L1. Then you take this, and then you write down this square, and then you want to say something about the induced map from the push-out of these two maps over here to this map, to this object over here. Maybe you want to say that it belongs to the class L2. So what is the appropriate sort of way to state this in the setting of algebraic Weak factorization systems? Well, I think a nice way to think about this is actually as these things as actually living as the squares in a certain triple category. So, I mean, I'm not just going to talk about double categories, I'm actually going to talk about n-fold categories for arbitrary n. And these squares, I imagine that these squares are actually the squares that actually live in a suitable triple category. Indeed. So, I think to actually formulate this, have an elegant formalism for this, I just have this ad hoc notion, in some sense, of an n structure. So an n structure is an n plus one-fold category with one dimension sort of singled out. So I think of these n structures as some sort of categories of n cubes, and then there is one dimension which is like, it gives the direction of the morphisms of n cubes, and that is this specified dimension that I'm talking about. So the case of double categories is the case where n equals 1. Okay? So you think, and in the case of double categories, the specified dimension is the horizontal dimension. So I think of this n plus one-fold category as having one horizontal dimension and having n vertical dimensions. So if C is a category, then we can find like an n structure of n cubes in C. I mean, this is just a straightforward generalization of the squares. And by an n structure over category C, we just mean an n structure L together with a morphism of n structures from L to the n cubes. And what we've done here is, well, if L is a left double category of an algebraic Weak factorization system, then there is like an n structure of cofibrant squares, of cofiber squares of L over C. So what you could imagine is that so here we have the n cubes, and then you can take like a big push out, and then of all the vertices, especially except for like the final one, and then this induces a map from this push out to the final one, and then we can require that to belong to this class L, and that gives me a new n structure, which I will write like this. So crucially, there is a certain kind of way of sort of combining an n structure and an, or let's say an n0 structure and an n1 structure into an n0 plus n1 structure. So this is basically because of the cubical combinatorics. So if you have an L0 is an n structure over C, L1 is an n structure over D, then there will be an n0 plus n1 structure, which will write L0 tensor L1 over C times D. And this we can use to define a certain multi-category. So what is this multi-category, or rather, let's say, a group-port-enriched multi-category? So the objects are finitely co-complete categories equipped with an algebraic Weak factorization system, and then a morphism from this n tuple to C is a pair consisting of a functor from C1 times C, this n-fold product, to C, which possess finite colimits in each entry. And the other thing that the pairs should do is it should give me a morphism of n structures over here. So this is an n structure, this is an n structure, because all of these things are basically double categories, so one structures, and so this becomes an n structure. So I want to have a morphism of n structures here, which makes this diagram neat. And then, so for two cells, I take natural isomorphisms between the f's, which sort of lift to the f hats. And then there's a very neat, crisp definition of what a monodal algebraic Weak factorization system is. It is simply a monoid in this multi-category. And I mean, in some similar style, we can define what an algebraic, like an algebraic monoidal model category is. So this is a definition which we came up with, which is a bit stronger than what Emily Real has defined earlier. So we both start, in some sense, from an algebraic model structure in category C. Well, that is consists of two algebraic Weak factorization systems, which will write like this. There is a certain, we want to say that every trivial cofibration is also a cofibration, that we can say like just the existence of a double functor. And then the underlying Weak factorization systems of these algebraic Weak factorization systems would give rise to a model category. So that is an algebraic model structure. And then if we want to say that it is an algebraic monoidal model structure over some monoidal category C, what we want to say is that, well, first of all, this C should be a monoid over this tensor. This T of C should have, like, I don't know, it should sometimes have an action from C, which also lives over this monoid. And then I want to have this map of double categories to have like a morphism which preserves this action. And that is Emily Real's definition of a monoidal algebraic model structure plus lots of extra conditions. So basically what I want to do is contain an algebraic Cartesian model structure on simplicial sets. Maybe the chair. How much time do I have left?
9 minutes.
9 minutes, okay. So what I want to do in order to construct this is I want to use effective confibration. So unfortunately, in the parallel development of Henri and Gambino, they've also used the word effective confibrations. And now I think we're both stubborn and we don't want to change our favorite name. But okay, let's say that we mean something different. So how are we going to construct these algebraic Weak factorization systems? Well, we're going to use a small object argument. And I want to have like a double categorical version of it, which fortunately exists. So there's something like in the paper by Berg and Garner, they say if I have a small double category, which over some locally presentable category C, then I can look at the things which have the right lifting property against this small double category L, and that will be the right double category in an algebraic Weak factorization system. Now the proof they give is classical, and of course the aim was to do everything constructively. However, I think it is this is something I'm looking at with one of my master students, so I think this double categorical version, at least maybe not at this level of generality, can maybe not be proven constructively, but in all the cases I'm interested in, this category C is a category of precies, my double category is countable, and the objects in the image of this, the objects basically in this double category are finite in some sense. So that should be good enough for all our constructive purposes. Okay. So let's start by constructing the effective trivial confibrations. So they usually have the right lifting properties against all monos. Or you could say inclusions of like sieves into representables. Now there's like a constructive nuance here. So I don't really want to use all sub-objects, but I want to use sub-objects which are point-wise decidable. So Basically, you could say that I want to, under you, look at those sieves, subjects of delta n, such that if I look at the m simplices, then this is a complemented subset of this thing here. So basically, I can see whether or not a certain map belongs to the sieve or not. Okay. Alright, so let's call these things cofibrant sieves. So these cofibrant sieves can be organized into a double category. So the objects are the cofibrant sieves. The horizontal morphisms are, from S to T, are going to be pullback squares. So there's like a map from, so this is a sieve on delta n, this is a sieve on delta m, then, basically, the horizontal morphisms are pullback squares of this form. Vertical morphisms are just inclusions of cofibrant sieves, and then a square, well, a square is, I think, the pullback square of the form that I think you can guess. So a square like this, I have another square like this, and then they should be sort of connected by another pullback square. And then I define effective trivial confiberations to be those things which are cofibrantly generated by this double category. I want to do something similar for the effective confibrations. So one way of doing this is actually to look at something we decided to call Horn-Boussage sequences. I mean, the idea is very simple. So I have like a sequence of cofibrant sieves, also like subobjects of some delta n. And basically what I want is that basically I get the next sieve by filling an horn in the previous sieve. Okay, so this basically just, by repeatedly filling horns, I can go from S0 to Sk. And then I define something like, then I have a notion of like a morphism of these Boussard sequences. So the idea is, if I have something which looks like this, in some delta n, I have something n which lives in some delta m. Then basically what I want is I want to have a map here, such that this is a pullback, this whole thing is a pullback, and then basically for everything here, there should be a map to something here, S of f of k, say, such that this whole thing is a pullback. So that I will call a morphism of Horn-Boussage sequences. And then basically these things can be organized into a double category. So the objects again are the cofibrant sieves. Horizontal morphisms are pullback squares like this, and vertical morphisms are Horn-Boussage sequences, and squares are morphisms of Horn-Boussage sequences, as in the previous slide. Now, I would love to be able to say that we now define the effective confibrations to be the things which have the right lifting property against this double category. This is not true for two reasons. Maybe in the interest of time. Sorry, how much time do you have?
4 minutes.
4 minutes. Okay. Well, okay. Ask me about it in the question time. Okay. So there are two additional things that we have to take care of. But this is roughly the idea. So how far are we? Well, okay, so first of all, the idea is that we want to have to really effectively construct something maybe which we hold relative to any elementary tuple, say, although I think I sympathize with the idea that we actually don't really need a subobject classifier, but we need something. So we want to construct an algebraic Cartesian model category on the simplicial sets in which the effective confibrations are the fibrations and effective trivial confibrations are the trivial fibrations. So basically I think there are two things which are left to do. So one is, okay, we have to finish this, we have to convince ourselves that in all cases of interest we have a constructive account of this small object argument which works for double categories, that I'm very confident that that's just a matter of sitting down and doing it. And then, as people probably know, who have followed sort of the developments in homotopy type theory and how to construct models of type theory constructively, one of the key steps is to prove some equivalence extension property. So in the masterpiece of Lingouanier, he formulates something he calls the more equivalence extension property. And basically, that's the thing that still needs to be proven, which, I don't know, I'm hopeful, optimistic, but I mean, this is way more difficult, definitely, than in the other point. So yeah, maybe I will stand here again next year at the next CT and I'll say that I've done this. That would be nice. The notion of effective confirmation, our notion of effective confirmation was introduced in a book I wrote together with Erik Faber, this one. So these are two preprints together with master students. They're both doing PhDs at this moment, but not with me. You can find these preprints on the archive. And so Lingouanier, in his masterpieces, you can also see lots about these things about monodal algebraic refactorization systems he defended last week. But I'm not sure if his thesis is already online, but it should soon be online. So that's what I wanted to say. So thank you.
Perfect timing. Questions or comments? Yes, there's one there.
Can you briefly explain the difference between your effective conflagrations and their effective conflagrations?
Okay. Yeah, so the question is like, what is the difference between the effective conflagrations of Henri and Gambino and mine? So I would say their notion of an effective conflagration is in some sense just an algebraic conflagration. It's just a map equipped with the additional structure of a solution for every Horn filling problem. So if you just give me a square with a Horn on the left, then it's equipped with a function which gives you a solution. The idea here is that we don't just want a solution, we want the solutions to satisfy certain compatibility conditions, which are sort of like formalized or like captured by formalized by this double category. So it's definitely the case that so we are way more sort of strict than they are. There's also the notion of a uniform conflagration, which was also introduced by Gambino and Sattler. There they do have this idea of having compatibility conditions, but these conditions are less strong, at least, okay. Our notion implies theirs. I don't know if the converse holds, I suspect not. Constructively.
I just wonder, are you planning to construct a model of homotopy type, univalent type theory using these effective conflagrations?
Yeah, that will be next. Yeah.
Another question.
Have you investigated the algebraically fibrant objects?
The algebraically fibrant objects. You mean like the effective complexes? No.
Yeah, I guess so. Because they're could be time complexes, which is sort of like infinity cuboids, but with some additional equations.
So basically, so there are like Hahn complexes, like algebraic Hahn complexes, where lifts satisfy additional properties. One thing, of course, that we always prove is that we want our count to be classically correct. So it should be the case that if you use the log exclude the middle and the axiom of choice, you can always prove that every Hahn complex in the traditional sense can be equipped with the structure of an effective Hahn complex. But there are certain instances where things get this structure sort of like out of the box. For example, one thing that we did with Freek, is that, for example, there's a result which says that simplicial groups are Hahn. So this proof is constructive, so you actually really get fillers. And if you organize things correctly, they will actually automatically satisfy this effectivity condition that we have. So that is also in this paper. So.
Something that was very useful in doing a constructive version of the cubicle case for this was having the fibration and trivial fibration structures be actual structures which are classified by objects of structure on a given map. And then those classifiers are stable under pullback. You hum into them to get the structure. And that's an idea that's coming from Mike Schulman, and he uses it in the, as you know, I'm sure.
Yeah.
In the thing, it's called a locally representable notion of fibered structure.
Yeah.
It's also something that Thierry has exploited.
What?
Are you using this at all?
Yeah. No, I mean, that's definitely very important. So, so our notion is locally presentable in that sense. And actually, this is one thing which is a problem with the, for example, uniform configurations in simplicial sets. So they're not locally presentable. There's a proof by Christian Sattler, which you can find in the book. Also, Andrew Swan has shown this. So this is actually one of the main reasons why I think why people have abandoned the uniform configurations in the setting of simplicial sets.
Let's thank the speaker again.